All right, our final talk for this session is Ron Yurko. So Ron Yurko is a PhD student in the Department of Statistics and Data Science at Carnegie Mellon University. In addition to his statistical methodology research oriented towards applications in genetics and genomics, he is actively involved in statistics and sports research. He is co-organizer of the annual Carnegie Mellon Sports Analytics Conference and reproducible research competition, and has developed multiple R packages to enable easy access to publicly available data, such as NFL Scraper. So join me in welcoming Ron. Okay, good. It's going to say we have the on that.
All right, we're good to go. All right, good morning. So 2 years ago, I began my NESSIS presentation with a rather bleak statement about the state of football analytics. Now in 2019, I'm very proud to think that things have definitely improved. And in large part, this is due to Max Horowitz creating the NFL Scraper package in R. And this has allowed people to access play-by-play data quite easily through R. And we've seen websites such as The Athletic, 538, feature data from our package and using the models we have. And this has inspired individuals to do this on their own. And as Ben Baldwin termed, the dark NFL analytics web that you see on Twitter. And if you've spent any time on football analytics Twitter, as crazy of a world as it is, you see that nearly most teams actually have a Twitter account solely dedicated to them, even the Miami Dolphins. So it's pretty exciting. At the core of this package are discrete time play value estimates using expected points and win probability models. So expected points and win probability, just as a brief recap, given the current situation, how many points am I likely to score? That's expected points. In our NFL Scraper model, we use a multinomial logistic regression approach. So our random variable is the next scoring event. We get probabilities for each of those possible events, and then just compute expected value with the associated points. And then that's fed into a generalized additive model that's a smoothing function of this expected score differential, along with some additive terms regarding timeouts, et cetera. So this, though, is giving us between play value. We can compute the expected points to win probability at the start of a play, and then the difference between the following play, and we get our expected points added, our win probability added. But what we really want is continuous time within play value to understand the movements that take place within the game of football. So the standard for this is the work by Cervone and the Bourne Lab in basketball. And so this is a figure from their paper showing you that expected possession value over the course of a single possession in basketball. You see the movements taking place, passes and whatnot, ultimately arriving at a LeBron James shot attempt. All right, so this is actually showing a sort of stock ticker movement, encapsulating the continuous time value. This isn't just the start of a play, end of a play. It's everything that's going on in between. And this has been extended into soccer as well. So for the longest time, there wasn't this data available for football. And the data that was proprietary. Enter the big data bowl. And so this is an exciting venture spearheaded by Michael Lopez, where for the past so many years, most of you are probably aware of this, the NFL has been collecting tracking data via chips in the shoulder pads and more recently the ball. But originally, not even teams had all access to it. But now, with NFL Director Michael Lopez, things have changed big time. And it was a very awesome event last year, the Big Data Bowl, providing the first 6 weeks of the 2017 season for people to enter in this competition. You're going to see talks later today focus on those entries. And they were primarily geared towards identifying receiver routes and whatnot. But there was also a call for a special issue, JQAS, using this data. So we took this as an opportunity for ourselves to see, okay, using this tracking data, what can we do? How can we take what's been done by Cervone, Bourne, and apply it to football? So what does this data actually look like? So you literally get the on-field X, Y, the speed of all players for at the 10th of a second for every play. So in this subset of data from the first 6 weeks of the 2017 season, this corresponds to a little over 14,000 plays and about 1 million unique timestamps. And the NFL also provides event annotations, such as when a handoff occurs, when the end of the play, when the ball is arriving on a pass, etc. So this is an example of a play that I'm going to use throughout my talk. It's a jet sweep touchdown run by wide receiver Cordell Patterson. Took place in a Raiders-Chargers game. And you see, okay, you get the XY of the player, you have the speed, direction, and then the event denoting. So this is the actual animation then of this jet sweep touchdown run. So besides the fact that's cool looking, I'm just going to say, I'm going to use this type of animation throughout, where the blue circles denote the offense, the orange denotes the defense, and then the ball carrier is denoted by the black dot. So you see her taking place. Patterson's getting the ball, a handoff, and he ultimately runs all the way to the end zone for a touchdown. So right now, we have values for the snap, and we have values for the touchdown at the end. We want to get the continuous time values, what's going on in between at the moment of handoff, at the moment of first contact. What do we expect to happen during that play? So we're going to take continuous time value framework, going to denote throughout the play the time t. And ultimately what we're interested in for football, all we really care about is the ending yard line of the play. That dictates what's going to be the next down, what's going to be the next yards to go situation, et cetera. We don't need to know the exact XY coordinate that the player is going to end up at. We really just need to know the X along the field. What's the yard line? So we care about modeling that end of play yard line. We're going to do this within the time t, and where I'm going to represent all the information I have, this filtration of ball carrier location, player locations, speed, trajectory. All this means is what information have I observed up until this point t. And I just want to model then the expectation of this end of play yard line given this filtration of information. So could we do a general framework for any play? This was throwing this in here, this is largely Sam Ventura's idea of going about a full framework. Sam likes to think big. So this took months of discussion within our CMU group, the idea of any type of play, the route what can take place in terms of decision making, how can you model going from passing to who's being targeted to just, okay, handling whether or not it's caught or intercepted, et cetera. Ultimately, though, everything in the end comes back to a ball carrier model. Once someone has the ball, where are they going to end up? The X, predicting that expected end of yard line, giving your information. So that's what I'm going to focus on today, and I'd be happy to talk offline more about some of these other pieces we've come up with. So the ball carrier model, explicitly, we're going to model the yards gained from the current moment on the field as some function of this filtration of information. And then since the yards gained from the current position plus the player's current position equals the end of play yard line, linearity of expectations, bam, we have our quantity of interest. So that's what we're doing here. We're just directly modeling the yards gained from the current spot on the field. We decided to take a kitchen sink approach and basically throw in everything we have available to us into the models we were going to test. So we look at all information corresponding to the ball carrier, the X, Y, the speed, as well as all the offense and defensive players. And then for each frame, we order the offense and defensive players based on Euclidean distance to the ball carrier. So defense 1_X corresponds to the X of the closest defender to the ball carrier. Defense 3, the third closest, and so on. We also decided to take a look at summarizing Voronoi tessellations, since essentially these are capturing the regions of ownership that players have on the field. So that's what this figure shows here, is this is that Patterson touchdown run at a point where Patterson, the black dot, his Voronoi includes the end zone. So we could take what's the X closest to the target end zone of interest as a covariate, what's the X that's further away, and then we also look at the area. Now I'm going to point out that this was really just a starting point of summarizing the Voronoi. There, you could do weighted Voronoi, encapsulating for speed, direction, et cetera, that we would like to do at some point later on, but this is just what we started with. So there's really 4 characteristics then of this ball carrier model. One, it's a high-dimensional problem, obviously. You have a lot of information where players are out in the field at all points in time. It's going to be nonlinear interactions between these variables. You can think of the fact, okay, the distance to the closest defender, where's the distance to the closest teammate, the actual XY. Can we somehow relate that to the blocking that's taking place? And the 4th characteristic really is there a temporal structure to this data? Is there some information knowing previously over the course of a run that helps me predict where it's going to go later on? So we then consider these various types of models to test with. So the intercept only is, there's no variables at all. I'm just going to take what's the average yards gained in a particular frame. This gives me my baseline to compare my other approaches with. Lasso, just throwing everything in as a linear model. It's probably not a fair comparison, but it's just a good baseline to start with. If I really did more proper feature engineering, then I could really consider the lasso as a comparison to these other flexible approaches. So this is XGBoost, which is just sum of gradient boosted trees. So you have many decision trees capturing a bunch of nonlinear effects and interactions. The title of the talk is Going Deep, so of course there are deep learning models. We tested comparing a feed-forward neural network along with an LSTM model. And the LSTM is the only one of these that naturally accounts for the temporal structure of the data. So we explored using lag variables as well for these other approaches, but we did not find them adding much to the performance for those approaches versus not using the lag, in comparison to the LSTM, which naturally accounts for that. To compare these, we then take a leave 1 week out cross-validation approach. So every single frame of our data set is going to be held out and get predicted value for. And then this gives us a good way of actually assessing out-of-sample performance. We're interested both in the overall error, as well as we don't want to see any bias over the course of the run. I don't want to necessarily be, oh, great predictions at the end of the run, but I'm really bad at the beginning. I want to have good predictions throughout the entire sequence of a ball carry. So that's what these figures are showing here. To break these down, each panel is for an individual model. The numbers, the RMSE that's displayed, is the overall error rate. So the LSTM is displaying the best performance. Then within each of these panels, the x-axis corresponds to the frames from the start of the ball carrier sequence. So x equals 0 means this is the start of the run. What is the y-axis corresponding to the RMSE at the start of the run? So naturally, the baseline is doing best over of its performance relative to the other approaches at the very beginning of a run, when not as much information has been observed. Once you start to get more information over the course of the run, you can really see the improvement of the performance of the LSTM versus other models. And the XGBoost model as well performed relatively well. But you see the lasso, especially at the end, and also the feed forward, really decay in performance with just this RMSE value. We additionally, to show this bias over the course of the sequence, this is the same figure with the x-axis being the frames from the start of the ball carrier sequence, but now the y-axis is just the actual residual value. And the points I'm displaying are the means with plus or minus 2 standard error bars. So the baseline, this intercept only, you can see the bias it has. It's not, what we want is something that's just right around 0 the whole way throughout. Right? So taking no variables at all, just taking the average, you're seeing bias, no good. The LSTM, relative to the other approaches, holds well across all lengths of runs, which is what we want to see. So ultimately, this is the approach we're taking. This is the model we're going to use throughout. So now we're going back to the example play, and this red line is showing the predicted end-of-play yard line. So you can see throughout the course of this run, from the start, as he's already moving in motion, he's already expected to have a solid gain, and it increases steadily after the point of first contact up until it gets to a touchdown. So you can connect this then to the actual variables in the models. So in the bottom left, that's the change we're showing into the distance to the closest defender. So at the point of first contact, you see it's above 0. Welcome to the world of tracking data. It's not perfect. And then the bottom right, you see the change in the ball carrier speed over time. And one of the nice things about this run, Patterson is maintaining a relatively high level of speed from handoff all the way to the touchdown. being the jet sweep that it is. You can really see it's once he has the point of first contact, to which then the distance between him and his closest defender keeps going up steadily. That's also when that point in time, when that red line just steadily increases and goes away. And then it starts to come back a bit once defenders come close to him. So now with this, we can actually formulate the stats in terms of evaluating players and teams with regards to this expectation. So instead of just looking at the yards gained on the play, how about, okay, given the information we've observed at handoff, what are they gaining with respect to that expectation at handoff? Are the players adding anything besides any of the information, all the other information I've already observed? Same thing with how many yards is the player adding after that point of first contact? And we can define new success rate measures as well. If we're expecting them to get a touchdown, expecting them to get a first down, are they actually reaching that point? This figure then is showing you y-axis is the average yards gained per attempt, so typical stat you'll see. The x-axis is the average yards gained above expectation at handoff per carry. So that's why you see this nice split right down the middle, the zero line, half the players above it, half below it. And so now we can actually differentiate players in this first 6 weeks of the season. So top right, Collins led the league for the first 6 weeks in yards gained per carry. He's located next to that player that shall not be named from the Chiefs. He is on the same vertical line as Devontae Freeman, Marlon Mack, Chris Thompson in terms of his yards gained above expectation at handoff. All right, so if we had more data, maybe we could test that to see is this something that's more stable, predictive over the years and over the course of the season. And just because I'm from Pittsburgh and I like to pick on the Bengals, Devontae Freeman, you could see, is although he's averaging the same yards gained per carry as Giovanni Bernard, he's averaging more above expectation at handoff. So with more data, maybe we could see that that's more predictive going forward as well. I'd like to think that Devontae Freeman is better than Giovanni Bernard. So we still ultimately want to have continuous time value estimates. So we can take our end of yard line prediction, and I could feed it into my expected points and win probability by just updating those covariates, updating that X design matrix. Get a new yard line, get a new down, get a new yards to go, update the full thing, and then I could feed that in, and now I'm going to get point estimates for my expected points, given the current information I observed at time point t. So this is just showing that multinomial logistic regression model, give my new X update, get new probabilities for different scoring events, and now I have this point estimate for expected points, and I can do the same thing to get a point estimate for the win probability. Now one thing I'm just going to point out here is both of these models would rely on time, and I'm cheating and just putting in the observed time. Really, you probably should model jointly both the yards as well as the time. But for now, we're just doing the yards. So this is then showing you the same thing with the top figure of the predicted yard line over the course of the run, but now I have the stock ticker, the bottom left being the change in the expected points, and the bottom right being the change in win probability. So you can see after that point of first contact, the steady increase in expected points goes up, ultimately until the moment where I think he's going to get a touchdown. And you see that same increase in win probability. The Raiders, I think, were actually down by 4 or 5 points in this game. Touchdown gave them the lead. They're more likely to win. Now, there's a problem here. So a word of caution about this. These are point estimates. All right, these values I'm feeding, I'm taking an expectation of the end of yard line, and I'm feeding it into these models. These expected points in win probability are really nonlinear, discontinuous, discrete. They're problematic utility functions. These are not the expectation of the expected points and the win probability of the course of the play. You could think of the way of if it's a situation the running back gains 1 more yard than expected, positive expected points might be meaningless in some sense. But if it's a 3rd and short situation and the running back fails to get the yard that I expect, now he's really going to be hit with negative expected points. all right? So it's not really appropriate to just take in these point estimates and start observing expected points and win probability values. And to really point this out to you, this is the same figure as before, with the y-axis being the average yards gained. The x-axis is just the EPA added above that expectation at handoff. So I generate some expected points given the handoff predicted yard line, and then I'm computing what expected points added above that handoff do I get from a player. Some people might think, oh, it's negative, that's great, rushing's bad. No, this is bad. This should still be centered at 0 along the x-axis. This is problematic from the fact that I'm just feeding in that point estimate. So we can't use this. So what do we do? So I've spent this entire time talking about predicting the end of yard line with this expectation using this LSTM model. And there's value to that, just knowing, okay, how many yards can I expect them to see above handoff? Really what I want to do is have some full estimate for the distribution. And I could take some, I could parameterize this in some way, say, force my field to be between 0 and 1, use a beta regression. I'm going to run into problems there. I really rather do something flexible and non-parametric. And fortunately, I am surrounded by smart people, one of which my co-authors, Taylor Puspissel, his dissertation was on conditional density estimation. And he implemented random forest conditional density estimation. That's what this animation is showing you here. So given all the same covariates that we use it for predicting the end of yard line, now I'm estimating a density curve over the field. So rather than getting a single red line on the field, I'm getting for each possible yard line a density value. And so I'm displaying that based on the darkness of the red. And what you're really seeing here is actually a prediction of a bimodal distribution of where the player is likely to end up. So at the start of the run, we see it gets very dense at the beginning of the first point of contact. And then over the course of the run, you see the red line at the end of the yard line start to really darken. Because now we're thinking, hey, Patterson might make it all the way to the end, or he's going to get tackled nearby. Oh, but he's really going to make it all the way to the end. Right? So that average, that expectation, that's a problem then for feeding into getting the expected points and win probability, those complicated utility functions. Now, though, instead, I want to take this approach. I can integrate over to get a new expectation value. But that is for another time. So to recap, we introduced a general framework we believe that can be extended to use for full continuous time valuation in football. And what's been great is there's been a lot of other work recently in this space. There's been the deep QB model introduced by Brian Burke for QB decision making, expected hypothetical completion percentage, completion probability from Deschamps and Evans. And the idea is these models, these approaches, could be taken in and plugged into the framework. And we also introduced a way of them modeling the expected end of yard line. And there is still some use to this, but we really think the approach is to do a conditional density estimation to get the full curve if we won expected points, if we won win probability over continuous time. And what's great is not only does Taylor have implemented a random forest conditional density estimation, he has deep CDE, meaning we could take an LSTM model for conditional density estimation as well. So obviously, we also want to implement the full framework at some point, and this was really a starting point in terms of the features we explored. You can do a much better job at creating variables to, say, have a linear model that's going to perform probably close to what we're getting if you construct it in a more proper way, especially taking advantage of the information that's in a Voronoi tessellation. And with this, we could then proceed to evaluate players at the continuous time level. Take good old regression approaches at their contributions within the frames to see the movements taking place, how much moving in a certain direction, moving at this certain speed helps the team, et cetera. And I should say, all this work is possible because of one man, Mike Lopez. So a big thank you goes out to him for providing the big datable data and calling for this special issue of JQAS. And I'm truly grateful, and I'd be even more grateful if I had all the data. And I'd just like to thank then the rest of the team that worked on this, Francesca, Lee, Nick, who's here, Taylor, Costas, and Sam. And be sure to check out our conference in the beginning of November. Thanks.
Are there any questions for Ron?
You talked about using the conditional probability density estimation. What about using the Bayesian as an inversion to give the distribution?
Are you using a Bayesian method?
Bayesian as TM.
Yeah, I mean, that's another approach. The one thing we explored also was you could generate even just basically standard errors within an LSTM to get an estimate on your, it would still get an estimate on your expected yard line. But yeah, absolutely, we can explore that as well.
What kind of time-related covariates did you construct? Because you kind of even mentioned it yourself, you might want to do this jointly with time and the yard expected, correct?
Well, the time would be something that's updated in terms of you're predicting where the player is going to end up. Would you predict also how long is it going to take for them to get there? Yeah, we didn't do that. We didn't predict how long. We just decided to take what was the observed how long.
But you would need to do that if you wanted to do some CDE on the expected.
Yeah, if you wanted to do it like in real time, absolutely. We're doing it in retrospect. Yeah.
We have time for one more question.
Lori?
Is it possible to use your method to sort of simulate forward optimal trajectories for a player to see, you know, how can they maximize their expected yards gained?
Yeah, absolutely. I think that could be something, an extension of this.
All right, let's just thank Ron.